students start working with density as early as the elementary school. The variables of the density they should know, you should know. The first variable that we need to be aware of is it involves mass. In the international system, the units in mass that we deal with are primarily the gram and the kilogram. Now, these units are called extensive variables. And let me give you a way to know what this means, extensive. Sounds like just sort of a junky word. Here's a question to always ask about a variable. If I say, what is the mass of aluminum? What is the mass of aluminum? So what do you mean, what is the mass? It depends on how much you have. What is the mass of aluminum? That's extensive. It depends on the amount. So in a variable that depends on the amount, it's called extensive. If we take the second variable that we deal with in density, it's called volume. Volume. The units for volume are the cubic centimeter, which is equivalent to a milliliter, and cubic meter. We will not deal with cubic meter very often because it's too large of a unit for us. The ratio of mass to volume is the operational definition of density. Operation means divide mass by volume and you get density, and you can see the units. Now, as we said, this one's extensive. And what is the volume of aluminum? We don't know. But if we say, what is the volume, or what is the density of aluminum, we do know that answer. Depending, no matter where we are, what country, if we say, what is the density of aluminum, we will see, and if you look at this chart that we have up here, the density of aluminum is 2.7 grams per cubic centimeter. That is a low density element compared to some of the very dense elements of gold and even osmium, the highest. Of course, it's much more dense than a gas. Now, the variables. You're going to be asked to solve for problems, and we can solve using an equation. That's the equation. Density is mass per unit volume. If we want to solve for mass, we could multiply both sides. Well, let's do it this way. If we multiply both sides by volume. See that? And then we have mass equals volume times density. If we wanted to solve, let's see, this is solving for density. Here we're solving for mass. Now we want to solve for volume, and I'll rewrite this equation here. We simply divide both sides by density. Density is gone here, and it's right here. So volume equals mass divided by density. So in an equation, always remember, you can solve, depending upon the question of the problem, solve for 3 different variables. Now you'll notice density for a particular substance is going to stay the same. We have a chart up here that shows you that no matter what the ratio of the volume to the density is we pick, the density of a substance here is going to be 1 gram or 1 unit per volume unit. In terms of pure substance, we introduced it, we better say something about it. If you start with all matter, which has mass and occupies volume, we can subdivide it into pure substances and non-pure substances. Pure substance has the same composition throughout. It will look the same, but the most important thing is the same composition. The only pure substances that we deal with are the elements, and when we combine elements into compounds. Everything else is a mixture. Densities don't have much meaning when we get the density, say, of a toy truck that has rubber and plastic. Compounds, there's millions of them. So the main thing density works with in identifying substances is with elements. For instance, let's take the aluminum. If aluminum's density is indeed 2.7 grams per cubic centimeter, let's see how it could be solved. If we did an experiment and we get a mass of 27.1 gram and the volume is 10 cubic centimeters, the answer is going to be 2.7, not 2.71. Now why? Because the numerator, right here, the numerator has 3 significant figures. And the denominator has 2 significant figures. The answer cannot be any more significant than the least significant starting point. Hear that. This is 3, this is 2. The answer has to be 2 significant figures. The answer in this case has to be 2. Many times we call them sig figs. Sig figs. The last thing I want to do is just talk about conversions of these units. If we want to take, I'll switch to gold. We'll put the chart up on gold. If you can look around there, down near the bottom, you see gold is 19.3 grams per cubic centimeter. If I want to convert that to kilograms per cubic meter, I have to multiply the denominator, or I want to get rid of grams, so I put grams in the denominator, it's gone, and kilograms in the numerator. And the unit is 1 kilogram is 1,000, 10 to the 3 grams. Then I want to get rid of cubic centimeters. Well, let's look at a picture of a cube very quickly. There is a cube. This is 1 meter on edge. 1 meter is 100 centimeters, 10 to the 2 centimeters. 10 to the 2 times 10 to the 2 times 10 to the 2. This means if I want to get rid of centimeters, I put it in the numerator, and that's 1 times 10 to the 6. Cubic centimeters is 1 cubic meter. And what do I have left? I have 19.3 kilograms, 10 to the 6 divided by 10 to the 3, and 19.3, and let me erase this right here. 19.3 times 10 to the 3 grams, or kilograms per cubic meter, rushing at the end there. 19.3 times 10 to the 3 kilograms per cubic meter. Okay, we will stop right there.